Okay, so I'm Eric Eilertson. I'm a security architect at Microsoft.
And I'm still Thordur Bjornsson, security engineer at Google. So yeah, that's we had to fix that. We found out that the words audits and assessment have a triggering effect on product managers at various vendors. So we are calling these reviews from now on. So anywhere in the slide deck that you see audit, just please mentally replace it with a review.
So for the agenda, we're going to go over some updates since 2022. Then we're going to go over the firmware security review framework. A little bit of a talk about some pilot programs where I've gotten this started, and then our call to action.
Yeah. So in 22, we did go in a little hibernation just because of lack of time and resources. But we did gather some initial feedback from vendors and auditors. And auditors in this case are what we call security review providers. These are third-party companies that provide review services. The process is ready for feedback. The framework document is published on the wiki. There should be a link somewhere in the slides to it. And we have one example scope for NVMe drives ready, and we are kind of, now want to get some more general feedback on how to do this, but we'll talk a little bit more about the framework itself. So the framework is small, and we want to keep it that way. It's a couple of pages, and it basically only describes what we want reviewed. And I do want to kind of hit on what we mean by reviews here. These are not certification process. There's not going to be like an OCP certified secure firmware. It's going to be a process that is very similar to the internal auditing that hyperscalers do, not only of their own components and software, but also the things that we buy from both OCP members and the industry at large. And the main difference here is we are not going to write hundreds of pages of review criteria. There's not going to be a specific set of things that you need to review in your ROM, and you get a checklist, and then you can provide a pass-fail result from that checklist. For those kind of things, there are organization standards and schemes. FIPS is one of them, common criteria is another. And thinking about it, those processes are more focused on the what you should do when you're designing a chip. Like for example, FIPS, it's the crypto boundaries and all of that stuff. What we want out of these reviews is a focus on the how the code base is implemented. Is it defensively written? Is it written in a modern language? Is it using modern standards of software development? Is it does it have adequate testing, not for like compliance towards functionality, but generic, good unit tests for helper functions that are, moving data around? Does it have good enough coverage of negative testing? You see that a lot in code bases, that the happy path is all tested, right? You have the thing that, checks the signature, verifies the certificate, passes on to the next boot stage, but it's completely missing any test of like, there is no signature, or the signature is invalid, or the certificate is expired, or whatever. That kind of unhappy path is almost always missing. And we want to do this in a way that is quite open. We want the scope, basically the framework, the point of the framework document, aside from helping us pick auditors, which is an ongoing effort. We are not really sure how to essentially qualify auditors. It's basically to give these kind of guardrails. And from this framework and the guardrails that it has, it is expected that the device vendor and the security review provider negotiate a kind of standard statement of work deal, and out of that is the scope of the review, and that is one of the publishable artifacts, and then the review happens along with specific findings. We are also looking for this kind of general commentary you get from these third parties. It's very common to see when they have found like a class of issues, they will then generally say that like this class of issues exist in the code base and should be remediated. And we are kind of after, at least in the first few reviews, of gathering those classes and kind of then extend the guardrails. The other parts of the framework is the guide for the retesting and time boxing. One of the problems with security reviews is they suffer from the infinite time, infinite money problem. There is no certain amount of time you can do a security review and then be happy that there are no issues. The only thing a security review really tells you is that that specific review found these issues. That, the absence of evidence is not evidence of absence, as Sagan said.
Yep. So one thing I'd like to add here is, from a security point of view, you should never have to trust a single entity. You shouldn't have to trust, the chip provider. Yep, we did a good job on our firmware. You shouldn't have to trust your cloud provider. Like, yep, we check everything, it's all good. You shouldn't have to trust a single entity. So one of the goals here by having this third-party audit is now there's at least 2 entities that have looked at the code base and done some level of effort and believe it is okay and trustworthy. So you're increasing the confidence that you're running good code. We've had a lot of talks on attestation, secure boot, all sorts of process and procedures to ensure you're running the buggy code that you asked to. So here's an effort to try to reduce the number and severity of the bugs in the code base.
So what do we want to review? I mean, realistically, the review process gets kicked off in 2 main types. It's either device vendor initiated, where they say, hey, we want to do a review, we found an auditor, all good. Or it's customer initiated, where, as a hyperscaler, we are buying, the new revision of the DCSEM card and want a firmware review of, the hardware components in it. Generally, we haven't spent a lot of time defining it. There's no need, really. It just needs to be sufficiently interesting. And, the pathological example is there's no secure review of, 20 megaohm resistors. So we expect devices that kind of happen through this firmware to be hitting some of these complexity highlights, which is they have an identity either through hopefully in the future, a Calyptro IROT. They have some ROM, they have mutable code, and they provide attestation. So the interesting bit there is the mutable code. It has firmware updates and things like that, where you are more interested in knowing what's going on and how it's being done. And it has some kind of management firmware. Not hard rules, but these are just guardrails. There are a few components that are dumb but active. Voltage regulators being kind of the primary example of those. And for those kind of things, and fan controllers, temperature sensors that are not smart in that way, but do they carry a lot of firmware? It's at scale risks of bricking. You can think of if you end up ingesting malicious firmware for your voltage regulator, it can play havoc with your devices. So yeah. So we organize the framework kind of around these pillars. Number 1 is documentation. And here we are going to start leaning on the device vendors to really present their threat model that they designed the device against and the firmware implementation. And how they are defining threat actors in their environment. And and kind of as a part of the scoping documents that would be as review artifacts, we are going to expect that those things are published as well. I think that has a tide that lifts all boats aspect to the OCP community and the public at large. Then, of course, there's the code assessment, or review, I should say there. And again, because of the kind of the infinite time, infinite money problem, we expect the scopes, and you can see it in the example scope that we have for NVMe drives, is that we are not very interested in the kind of the functionality of the device. If it's an SSD drive, there's not going to be any review that it can actually store and retrieve data. We kind of just take that as a given. What we are interested in that, and to kind of time limit the amount of effort that needs to be spent in the reviews, is the integrity story of it, or the secure boot story, and attestation mechanisms, if applicable. There are also some things in that kind of bleed into the manufacturing and supply chain, and that is the debug capabilities of the device. It's very common that you have the board, you can flip a jumper, and now you can load whatever firmware you want. You disable the signature checks, or you have a mechanism to initiate an RMA, or a return to manufacturer authorization, which might blow away all of your security because it opens the device back up for debugging, where the device vendor wants to take the chip or SoC that you ship back and try to figure out why you sent it back. In the supply chain, there is also the software component of it. And I really don't want to use the word supply chain when describing open source software or FOSS software that is being used in the code base we have, be it like embed TLS or whatever that's being integrated. That's a thing that we care also deeply about, and is a building block towards some future work. In the documentation, there's also, aside from the threat models, one of the things that we generally want to do as security practitioners when reviewing hardware devices is to get a volatile storage statement, which is basically, on this SOC, where is anything that can hide badness or allow persistence? And it is sometimes very difficult to tease that out. There might be, spy flashes or eMMC or what have you attached to the machine that is not easily documented because it's there for internal reasons of the firmware, whatever it is. And more often than not, we find that it can also be used to launch code, sometimes for debugging or just during normal operations. And these are kind of statements that we are very interested in having kind of attested from the device vendor. It also comes into being able to clearing them securely, secure erase for these volatile storage areas. That's very important for when you do RMA or kind of end of life the device. On top of that are what we call critical security parameters. And these are things like in straps or fuses that you can set on the board itself that impact kind of the integrity or behavior of the chip. And those are those.
So, talking about the integrity, looking at the code base, there are a few things that we want to be analyzed here. So, one of the big ones is it memory safe programming? Are there bounds checks on when you're handling with strings or copying buffers? This is where so many vulnerabilities and exploits come from, is poor coding practices. So we would like to have the reviewer look for the coding practices. Is there, if it's written in a newer language like Rust or Go, okay, that's great. You get a lot more guarantees there. But if it's written in C, you can still do a good job there, but you have to do some more work. So are they using appropriate functions and doing a good job with their managing memory? Another simple one to look for, are there hard-coded credentials? Is there a secret user? Is there a backdoor? Is there a password, something in there that exists, that we don't want to have? And also, are there any undocumented access channels? If it's documented, I can disable that. I know when it's on, when it's not. But if it's undocumented, I don't know how to mitigate and protect against that. So I would like somebody else to look and verify that there's no undocumented access channels. And looking at the secure and measured boot, is it all run through there? Does that code look good? Are there vulnerabilities? It's really looking at a lot of the coding standards and practices in the code base. Signature verification, looking at negative pass testing. Okay, a lot of people check the happy pass, but can I somehow trick it and then I can put, or I don't actually check a signature, or oh, I did something weird and I overflow and I can still run anyways. So let's really focus on the signature verification. Is there anti-rollback? How is that enforced and checked? Can I do some weird glitching? Is there a timing attack where I can get it to roll back and run an insecure version of firmware? Similar along with the recovery, and also debug enable it. Can I get to a point where I can know that a debug is disabled and cannot be turned on again without a reboot or a reset? Or what guarantees are there around debug? So then we get to attestation. What is the implementation of SPDM? Does it look good? Do they have a proper implementation there? Are there any known vulnerabilities? And, the CA, the final responders. So kind of look at the entire environment around SPDM and the attestation.
Just to add there, like the configuration and state, it's very hard for a spec like Calyptra as an IROT saying, oh, these things must always be included in dice measurements. It doesn't make any sense. This is very SOC specific. And then checking kind of the device vendor provided list of critical security parameters, and then having the review ensure that those are all present and accounted for in the attestation document. Because if debug enablement is simply not attested to, we might not know if a device transitions into a debug mode or not, which could be, well, critical to the security of the device.
Yeah, so many things are implementation specific, and that's where you need, or how did this chip get implemented changes what the firmware around it is going to do. And sometimes that's one vendor that could be important to look at that, another one, due to the way that a chip's been implemented, I don't really need to look at that parameter. So I would like somebody else to look at that and understand that all the security critical parameters are represented in the attestation report. And so then looking at the manufacturing and supply chain. So some of this is going to be what were their plans for field and data center and owner entropy, and so how do you get, what's your IROT, what do you have? Calyptra would be one nice thing. How do you manage and protect your DICE identity and your UDS? These long-term secrets, when they get brought in and used, do they get cleared right away? Is it sitting around in memory? Could some other portion of firmware have access to it? So how long do secrets live and are they protected? And so one thing that looking at is cryptographic key material. So yep, you can have a FIPS certified library and you're using all the appropriate algorithms, but then in between your calls into that, you crush your entropy, or you have something that's predictable, and now you've weakened everything. You still pass FIPS, but it's not secure. So let's look at how are you people using the crypt libraries, and are they doing that in a secure way? And then some of this gets back into like the software supply chain and the bill of material. Which libraries are you being used? Have those been looked at and attested or been reviewed already? As this gets going and there's more things that have been reviewed, embed TLS may have already been reviewed, and if you use somebody else that's already looked at that, great, you don't have to look at that again. You already have a hash of that, you're using that same hashed version of that firmware, we don't need to look anymore. So over time, the amount of work needed to do these assessments will be reduced down. Did you want to handle the...
Yeah, this one is actually kind of just a duplicate, but yes.
Yeah.
So let's skip it.
Okay. So on some of the pilot programs. So right now we have, there already existed the OCP NVMe boot specification, and so we added on to that, and we came up with a scope document for what we want to have looked at in conjunction with that boot specification. So Microsoft worked with SK Hynix as they're providing a boot drive for us, and with IOActive to do a review of the firmware and the boot drive, both physical. They hooked us up to all sorts of JTAG and debug, and they did a physical penetration testing along with a code review, and they identified, I think it was 4 security issues, 1 medium, 3 low. So then we worked with SK Hynix, and they fixed that and gave us a new firmware release. So right now, Microsoft is currently evaluating the drive and that firmware. Then we'll work with IOActive to have them do a review of the new firmware, the deltas that were done to that. And then we'll work with SK Hynix or with IOActive to publish what we're calling a short form report. So this would be a machine-readable JSON blob that has the hash of the firmware and a list of any vulnerabilities that are still in there, like a CVE score from like NIST would be one way to do that. And so this is meant to be something that you can use as part of the boot process, and then you can hand this up as part of your attestation so customers can know what version of firmware is running and what is all of the firmware that's running. So we're kind of going through a pipe cleaning exercise right now in Microsoft. How do we bring this in? How can, as we're testing and deploying firmware, how do we incorporate this machine readable, this JSON format to verify we're running the right firmware? And then with Calyptra on the horizon, coming soon, we will probably have a very large and intense effort to do a verification of the RTL, the ROM, and the firmware there. And we expect that scope will probably work on this summer and have that done and kick off the audit, or perhaps several assessments, I should say. So now for call to action. So we published a draft of the framework document and one example scope on the OCP wiki security page. And we need some feedback and comments. What would work, what wouldn't? Is there something else you need to see in there? And there is some debate on do we want to be prescriptive or descriptive in what these scope documents are. If you're prescriptive, you could turn it into a checklist of you have to check box this, 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 and this. But if I have a good review firm doing this, I would like them to go and look where they think there could be vulnerabilities and not just satisfy a checkbox. But then it's a qualitative, how do you enforce that? How do you know you're getting a good report?
Right.
And so there's difficulty there, and there's some tension, and some guidance, some input there would be appreciated. I guess, are there questions, comments? Yep. Mm-hmm. Yep. So, I mean, we would like the reviewer, first the vendor, we'd like them to say, yeah, we don't have backdoors. And then the reviewer is a second check on that, because I don't want to trust a single entity. I don't want to have to trust the vendor. I would like somebody else to also verify that.
Yes, but we are required to put vectors. We develop
Okay.
solutions, and we are required to put vectors. If we build a solution without vectors, it's not accepted. NSA
Yep.
will not accept any solution without the vectors.
Okay, right, yep. If that's the case, if that's your need, then that might not go well for a security review audit like this. And
Actually, another way to think about it, at that point, you're not really speaking about a backdoor. You're speaking about a different type of management interface. And if that one happens to be cryptographically authorized, and the private key is, handled securely by the government actor that uses it,
yeah.
I mean, it's fine. I'm not going to buy the device, but from a security perspective, if there is authorization on it, it's indistinguishable from another thing.
Yeah. So if it's a cryptographic, backdoor, you got a trapdoor function or something like that on there, then that's document which algorithms you're using and what they are.
No, my question is for, because this is an open computer project, yeah?
Yep.
And you say you don't accept anything with a vector, and that seems that everything in cryptographic is a vector, as a vector.
Okay.
If the vector not detected, it's another story. We need to hide the vector very good, that it's not detectable, then it's not a good vector, yeah? Because then we can hack it. And the question is how it works
No.
with the open computer project. Because even the quantum key distribution is a vector.
Sure. I think this just falls out of scope because I would expect this to be implemented in such a way that, like, on inspection of the device, you wouldn't see it. On the firmware that you hand over to the audit, it wouldn't be there, and then you would have to figure out how you deal with the measurement and attestations. But I would just scope out this problem and say, like, I don't care.
Yeah.
But it's an interesting train of thought, though. But yeah.
Alex?
So the framework that you're describing, like, puts significant guidelines around how to do this. Were you studying other frameworks that for security audits or security reviews that led you to these? Are there others that are similar that we should all be learning from?
So we've looked a little bit, so FIPS is mostly looking at like the cryptographic implementation. Common criteria has some, around the cryptography, but it goes a little bit into the code checking and quality, a little bit there. And so we're mostly trying to formalize a process that we've been using already for years, which is there's a device we're interested in, we hire an external company, maybe it's a couple $100,000 audit, and we get back a several hundred-page PDF document of the findings. If there's no findings, there's a lot of work put in that document to show we did the effort and we couldn't find anything. If it doesn't take them too long to find a bunch of vulnerabilities, then they can kind of quit early and say, we found a bunch of vulnerabilities, go fix these. So that's, in the specification we call a short form and a long form report. So this long form report is the 100-page PDF document that we've been getting for years that the reviewer company writes as part of their standard deliverable, their proof of work, essentially. And then this short form is a machine-readable one that you can be used as part of your boot process, your attestation. It can be handed up to a customer so they can know. So we're really, we've looked at some other frameworks, some other processes, but we're kind of trying to formalize what we've already been doing already. Yep.
One question is, for instance, you mentioned the themes. Like, I really like your idea, but I have one issue with saying with the scalability of solution because since you mentioned we have external audit, yes, we have dashboard this firmware, and then the company who is doing the firmware upgrade, yes.
Mm-hmm.
So if we upgrade, they will need to get another
Yes.
Yes.
do some part. And this is like many more companies start using this is the same with FIPS. More companies have a FIPS, and right now they do for FIPS like half a year at least, and it's getting longer and longer, yes?
Yep.
So I like the approach, but
There,
let's say the relation of maintaining it.
yep, there's definitely going to be, as we scale up and have more things run through this review process, we may need to have more review companies, more firms doing this work, and but also, what is enough of a change to require a review? Now, this is where if we have a hash of the firmware, any change that's no longer going to match. So one thought could be, if you're coming, I work at Microsoft, you come to Microsoft, look at, okay, what is your release notes? What did you change in this new firmware? Was some of it addressing bugs or vulnerabilities? Okay, well then I might want to look at that. If it's feature changes that don't have a security impact, maybe I let that one go, or maybe delay that a little while. So there's going to be, each company will have to make a decision on their risk assessment until we can scale this, and maybe hopefully we can gain some efficiency so that we can have this done systematically as part of just regular business.
This also becomes a very subjective assessment of the final report, and like for example, internally at work, these kind of reports are what I use as a basis to decide, like, oh, for this vendor, we want to review every single revision of their firmware, versus I don't care. I mean, they have a good test coverage, they do fuzzing, they have unhappy path testing, they're great guys, awesome. I'll review the next major version. But like on this other side of the table is, moral equivalent of Swiss cheese, and then I want to review everything all of the time. And that's very hard to capture in like a specification document, because it at the end is a subjective assessment of the vendor, the report, the quality of the documentation, and your internal usage of this chip. Like, if it's not in your TCB, then you might not even care.
Usually it's a couple of weeks.
10 to like 3 weeks is like the maximum we do, because at that point it becomes cost prohibitive. Yes. No. The entire point of this is to be like kind of our exportion of standard audit security audits, and they never take months. I mean, they might take months if you're thinking about like an entire chassis of a machine, then you want to review each component within it, but then the individual reviews are kind of time boxed too. I have never seen anything longer than 3 weeks. And it's usually less than that, in the sense that it's 3 weeks person hours. So the wall clock time is maybe a week or 2 weeks.
Any
All
other
right.
questions? Thank you very much.
Thank you.